We'll begin our exploration into similarity by discussing what makes polygons similar. So our job will be to identify similar polygons and then to apply that concept of similarity to calculate lengths of sides or measures of angles. And so in order to do that, we first need to understand what similar figures are. So similar figures are just those that have the same shape but are not necessarily the same size. And what we mean by that is not to say that all rectangles are similar and all triangles are similar, but there's a little more nuance to it than that. And so we want to make sure that we investigate that fully. Polygons are similar if their corresponding angles are congruent and if their corresponding sides are proportional. If their corresponding sides are proportional. And so the way that we will explore that is first by either being given that we know the lengths of certain sides or the measures of certain angles or markings for certain angles, declaring that they're congruent. We may also have to apply concepts from previous units, previous lessons, such as parallel lines cut by transversal make alternate interior angles congruent or corresponding angles congruent, and applying those concepts here in this conversation. And when we know that corresponding sides are proportional, that simply means that we have two ratios that are equal to each other. The length of the base and to the height of a rectangle and the corresponding base and height of another rectangle. If those are equal ratios, then we would say that those sides are proportional. Now that ratio of those corresponding sides is referred to as the similarity ratio. In other disciplines, you may call that the scale factor. All right, when you're looking at a map and the map is drawn, hopefully, obviously, to scale, there is a legend that indicates what the scale is. 1 inch on the map is equal to 20 miles in the real world, or whatever. And so that scale factor, that similarity ratio, is the language that we will use in describing that proportion, comparing the base of one triangle to the base of another, or the height of one triangle to the height of a similar triangle. That will be that similarity ratio. And so in this situation, there's a lot happening in this picture. So do your best to draw those pictures. We've got these two, what appear to be parallelograms or rhombuses, but we'll just go ahead and call them quadrilaterals for now. We've got A, B, C, D, and we've got E, F, G, H. We are saying that they are similar to each other. This notation means similar. And the order of the letters indicates the corresponding parts, just like it did back in our congruence units. And so in that exploration here, we can complete a couple statements. First of all, the measure of angle A is going to equal the measure of angle E. Those are corresponding angles. A corresponds to E, and therefore we will know the measure of angle A is going to be 53 degrees. Furthermore, when we are talking about the proportional nature of the side lengths, we're going to be referencing the fact that if these figures are similar, as is declared here using this similar symbol, we know that this side, AB, corresponds to and is therefore proportional to side EF. And so we have the length of segment AB to the length of segment EF is going to be equal to the length of segment AD compared to what segment? Well, AB goes with EF like AD goes with EH. And so we're able to fill in this statement, not knowing necessarily what the lengths are, but using the notation from our first unit together. Now let's see if you can extend this proportion to say segment or side BC corresponds to what? Go ahead and fill in that blank. And then also for us, go ahead and say the measure of angle F is equal to what measure? You can pause the video and fill that out as you want. Moving right along to our next example. We want to, in most of the work that we're doing, determine whether or not the polygons are similar. Sometimes we're told that they're similar. We're given the similarity statement. We know which corresponding parts go with each other. We can create proportions, solve proportions. We can write equations declaring that the angles are congruent and therefore their measures are equal. But oftentimes we have situations where we do not know whether or not the figures are similar, and our task is to determine whether they are. And in order to do that, we're going to try to explore a little bit about the lengths of the sides of these two triangles. So we've got triangle ABC, and it looks like we've got triangle DEF. And so we're going to have a little exploration here to find out, does the lengths of the sides of one triangle correspond to, and therefore are proportional to, the corresponding sides in the other triangle. And so what we're going to find here is that AB corresponding to DE, BC to EF, CA to FD gives us this situation. All right, we're basically saying, is this true? If these sides are proportional to one another, then these figures are similar. So we have 12 to 20, we've got 15 to 16, and we've got 18 to 24. Well, what we can find out pretty quickly is that these are not equal to each other, all right? We can show that AB to DE is not proportional to BC over EF. And so we can do that using the cross product property, or we can simplify the fractions. 12 over 20 has a common factor of 4 in the numerator and 4 in the denominator, and 3/5 is not equal to 15/16. Therefore, we cannot say that these figures are similar since the sides are not proportional. Furthermore, this is not equal either. 15 over 16 does not simplify, but 18 over 24 has a common factor of 6. That leaves us with 6 times 3 and 6 times 4. And these fractions are not equal to each other either. And so none of these ratios are equal. We don't need to show that none of them are equal. We simply need to show that one pair of fractions is not equal to say that these are not similar triangles. However, this simply means that triangle ABC is not similar to triangle DEF. All right? However, I've intentionally worked this example in the incorrect way. All right? One thing that I want you to know is that these two triangles actually are similar. All right? A lot of times we are convinced that we need to work in some kind of alphabetical order here with ABC and DEF. The way that the triangles are laid out is not actually the way in which this pair is declared similar. What we will find out, however, is that I can take the lengths of the sides, 12, 15, and 18, and I can put them over the sides in numerical order from smallest to largest, and it turns out that these fractions actually are indeed equal to each other. That we can show that 12 over 16 is equal to 3 times 4 over 4 times 4, that 15 over 20 is 3 times 5 over 4 times 5, that 18 over 24 is 6 times 3 over 6 times 4, and so all of these are equal to 3/4. Therefore, they're equal to each other. Therefore, those are proportional. But what we have here is AB, BC, and CA, or AC, however you want to say that, corresponding to segment FE, ED, and DF. All right? And so that means that triangle ABC is similar to triangle FED. And the similarity ratio, or that scale factor that we spoke about earlier, is 3/4. Or you can say 3 to 4. And so that is how we determine similarity. Or that is how, in the original part of this example, that is how we show that figures are not similar to one another. Now, applying similarity. If we know that figures are similar, that means that we know that their sides are proportional. We know that their sides are proportional. And so in this case, we would know that MN corresponds with RS. So this length goes with that length. The length of segment MN goes with the length of segment RS. So I can say 2 over x is going to equal the length of segment LO compared to the length of segment QT. And so I can create this equation, this proportion, and then we can do the work of the cross product property. 2 times 6 equals x times 5, and so 12 equals 5x, or 12/5 is equal to x. And that will tell us the length of that side. We could go ahead and actually write that as a decimal if that is fun for us. That would be 2.4, and then we would know the length of the top of what appears to be a trapezoid. All right? And the fun thing is that it really doesn't matter exactly how we structure that. If you're comparing the little one to the big one, the first one to the second one, that's fine. If you do it the big one to the small one and your fractions are flipped, that is okay. We're going to get the same answer of 12/5. Okay? And so it doesn't matter how we organize that. The key here is that we're comparing the sides in one figure to the sides in the other. All right, and that kind of concludes these examples. Our goal was to be able to identify similar polygons and then to apply similar polygons.